For the yeah, I don't know about the Minecraft movie, but for the Minions movie, yeah, and they're also like throwing bananas. It's all compared to his dudes. That's not great.
Okay, so let's get started. Good afternoon, everyone. Welcome to the AstroAI seminar. Today, I'm very happy to introduce Chris Lovell, who's in a marathon visit from the UK to the East Coast over the last few days, giving a bunch of talks. And he made some time today to visit us and present his work on galaxies and how to do forward and inverse, inference in galaxies. He put in here sort of a nice analogy. Galaxies don't evolve the same if they are in crowded fields versus if they're isolated, just like people don't behave the same in cities versus rural, I guess. Politically, I don't know what it is but anyway, he is currently at the Kavli Institute for Cosmology in Cambridge, the University of Cambridge. He got his PhD from the University of Sussex and has been mostly in the UK doing a couple of postdoctoral appointments, and now he's going to tell us about his work. So, floor is yours. I encourage everyone to interact with questions and discuss. Other than that, please take it up. Thank you so much. Please remember to scan that and do attendance because that way we get through. Thanks.
Yeah, thank you very, very much for the nice intro. I'm going to try and rattle through a few different things I'm doing in this general space here on novel forward and inverse modeling approaches. I realize there's maybe a mix of experience in terms of machine learning in the room. So if you'd like me to spend a little bit more time on something, then please just shout. But just sort of... My microphone is on. I can just start shouting though, if that helps. Is this better at the back? Not really.
I'll just speak up.
Okay.
It is on.
Okay, yeah. So to kind of set the scene a little bit, we have a huge sort of deluge of data coming through over the next few years. This is a deep field from the Euclid observatory showing this, some of the huge diversity of galaxies and environments that we're now able to probe. And we also have things like JWST probing, dense cluster environments in exquisite detail. You see this beautiful S-Max lens that was discovered in the first data releases, as well as this pristine IFU imaging data, which gives us incredible details on the chemical composition and dust makeup of these galaxies at unprecedented distances away. Complementary to this, we also have a number of simulations that are used to interpret and understand these observations and also to plan new observations and surveys. This is a dark matter only simulation from the Flamingo collaboration, showing this beautiful cosmic web structure. But we also have complementary to this. This has hydro simulations complementary to this that can actually probe the gas content of massive galaxy clusters. And also, as alongside this, we have these exquisitely detailed, resolved models of galaxies, individual galaxies that show the details of their stellar formation, hydrodynamics, et cetera, So a huge range of scales here that also matches those that we're seeing in the observations. And the actual physics that's going on in all of these objects is also inherently multi-scale and over an unprecedented range of scales. So from this sort of dark cosmic web scales here on the far right, galaxies are essentially composed of stars, black holes, etc. And the black holes, their accretion disks are almost 10 orders of magnitude smaller in scale, right? So if we really want to build a comprehensive and self-consistent model of galaxy evolution, we need something that can ideally resolve all of these scales, or at least understand the links between these scales in a more effective way. So I'm going to begin with this issue of this sort of volume that we can probe with simulations and the resolution or fidelity of those simulations. And if you look at sort of a number of sort of flagship models on this plane, you see that they generally follow this relation. Whereas you go to large volumes, you have to sacrifice the fidelity of the simulation, the resolution, and you also have to sometimes resort to just pure dark matter only n-body simulations, right? To the far right, we're here talking about exquisite radiation hydrodynamic simulations that can explicitly resolve the ISM, but are in volumes that are much smaller, orders of magnitude smaller than the kinds of areas that we're seeing now with these wide field surveys. So what we'd really like to do is probe up here, right? Or at the very least, what we'd like to do is be able to resolve all of the galaxies we're going to see with these wide field surveys, such as Euclid. And these tend to be those that are resolved with sort of 10 to the 6 M solar resolution, so 10 to the 8 M solar galaxies. And ideally, if we want to probe the ISM, the detailed ISM structure of these galaxies, we want to be probing down even further than this. So this is the challenge. And to really set the scene and show the issues here, so Eagle is a hydrodynamic model at around 10 to the 6 solar mass resolution. It's 100 megaparsecs on a side. And here, compared to the total volume probed by the Cosmos Web survey in Cycle 1. This is the total volume of all of the Cycle 1 surveys from JWST. And so we're still in the same kind of ballpark here. This is now Euclid-wide compared to those volumes, right? So we really are in a very different volume regime compared to these simulations. And when we're doing these comparisons, we need to keep in mind that the kinds of environments probed by Euclid simply don't exist in these, what are still quite large volume simulations at this resolution. So one approach that I'm going to try to sell to you today is to use zoom simulations. So zooms are a way of taking some region of interest from a large, lower resolution, say dark matter only simulation, and then resimulating just that region with either added physics or higher resolution. So this still includes then the large scale environment, the large scale modes of the matter distribution, but we're able to include a lot more of the physics we perhaps care about on these smaller scales. And so one approach that we did a few years ago to demonstrate this was flares. This is the first light reionization epoch simulations, where we essentially took this large dark matter only simulation, 3.2 gigaparsecs on the side, so equivalent almost to the Euclid sort of footprint. This is now compared here to the Eagle 100 megaparsec box, just for comparison. And what we did is we measured the overdensity distribution of this box. So we took some spheres and we basically randomly placed them within this volume and measured the relative overdensity of the field on those spheres. And you get out this sort of log normal distribution where, to the right here, we have these very overdense clumps, and to the left, we have these underdense sort of void-like regions. This is only at redshift 5, which will become more important later. And what we did is we then selected 40 regions with different overdensities here to kind of represent this whole box. So we particularly targeted very overdense regions, rare overdensities in the high redshift universe, where we're seeing now a lot of these extreme galaxies. But we also selected these underdense and medium density regions too. And what we did is then re-simulated these with the full hydrodynamics of the Eagle subgrid model. So these are our selected regions, they're spheres. So with zooms, you essentially, you have some boundary to the dark matter only sort of pressureless boundary. So you want to minimize the impact of that. So using these spheres actually reduces the surface area. The Eagle model is fully tested at redshift 0. It's able to reproduce broadly the galaxy stellar mass function, size mass relations, and Gregorian relation. We're now then taking this model and testing it in this high redshift regime. So in the high redshift and high density regime. So this has a kind of volume around 1.3 times that 100 megaparsec fiducial box. Oops. What we can do with these, because we know the overdensities that they're selected from, we can statistically combine these together to mimic the whole box, right? So here is just an example showing the galaxy stellar mass function from 3 of these different regions, an overdense region and an underdense region. And essentially, we know the average weighting or the average contribution of regions of that overdensity to the overall box. So you can just linearly combine these together. This is an example now of the UV luminosity function to reproduce these distribution functions on much larger scales. This is showing the UV luminosity function, so bright things to the right here, faint things to the left. The dashed line here is the 100 megaparsec Eagle volume I told you about before. And this is what we get with flares. Right? So we're able to probe these very, very bright, rare objects, whilst also simultaneously reproducing the behavior at the faint end down to these very, very faint and lower mass objects. The boxes here essentially are showing the relative depths and coverage of different surveys. So you can see now we're able to probe a Euclid-wide regime, whilst also simultaneously getting galaxies that are detected by JWST, these very, very deep objects. So flares has been going for a few years now. If you're interested in high redshift galaxy evolution in extreme environments, I encourage you to go and take a look at some of these papers we published recently. Ostensibly, we're in this sort of effective volume now in the top right of this plot, which is quite exciting. The caveat being that this is only down to redshift 5, right? So if we really want to probe down to redshift 0, how do we overcome this issue? Okay, I'm going to take a slight left turn now and think about another issue with these cosmological simulations, which is parameter spaces and the modeling choices that go into them. So most galaxy formation simulations, such as the Eagle one I just showed you, present a single fiducial model with some, fiducial modeling choices or some parameter choices. And there's very little modification or exploration of those parameter choices and the impact on the predictions. This is a nice plot from Mark Vogelsberger's recent review, showing a lot of the ingredients that go into these cosmological simulations and some of the choices that you have to make when doing these simulations. Okay, so from even the fundamental cosmological frameworks, your choice of cosmological model, etc., all the way up to your recipes for supermassive black hole feedback, star formation, etc., etc., etc. So very few of the flagship simulations, I don't think this is a controversial statement, very few of them explore these kinds of choices in a systematic kind of way. One suite that has attempted to do this is called CAMELS, which you may be familiar with. So this stands for Cosmology and Astrophysics with Machine Learning Simulations. And so the key thing here is that these are simulations that are varying large ranges of parameters and exploring lots of different, what we call subgrid models, specifically for machine learning applications. So there's a number of different suites here with different simulations. You have heard illustrious TNG, Simba, Eagle, etc., run in these relatively small volumes. These are only 25 megaparsecs on a side. There's a new suite coming, which will be 50 megaparsecs on a side, but this is still, much, much smaller than these wide field surveys. And they run them in these different sets. So the main one that is of interest here is this Latin hypercube set, where essentially they're varying 6 of these parameters. Some suites have more, but essentially 2 cosmological parameters, omega matter and sigma 8, plus 4 astrophysical parameters. So 2 describing the strength and efficacy of supernova feedback, and 2 describing the impact of AGN feedback. So these are essentially run, there's 1,000 simulations in this Latin hypercube set, where these are varied over this Latin hypercube. So each individual simulation has some random combination, essentially, of these parameters. And what this allows us to do then is start to look at the impact. So I should have said these are full hydro simulations using these illustrious TNG Simba subgrid models. We can look at the impact of both cosmology and the astrophysical choices on a lot of these galaxy observables. So this is the cosmic star formation rate density. This is a function of redshift. You can see the huge impact here of omega matter. The range of this parameter is quite large in CAMELS, but you can see that these cosmological parameters do have very visible differences or impacts, on galaxy formation. You'll notice that these AGN parameters don't seem to do as much. This is partly due to the fact that these are run in quite small boxes, so 25 megaparsecs. You simply don't have very many massive halos within those kinds of boxes where AGN has a big impact. Again, we'll maybe get back onto that in a second. So across all of these suites, these have been run. So there's over around 10,000 simulations here which can be used for various tasks. To kind of demonstrate some of the differences here, sorry, this is very low resolution from YouTube, but essentially what I'm showing here are 8 different boxes, all run with the same initial conditions, but assuming a different underlying subgrid model. The blue, you can barely see here, is the underlying dark matter density, and the red is the density and temperature of the IGN. And so the one thing to immediately take away is that all of these look quite different, right? So these are all run with exactly the same initial conditions. The only thing changing here is the strength, relative strength, etc., of stellar and AGN feedback. One kind of glaring example is Simba here, which blows these enormous jets into the IGN, which kind of heat up the whole box relatively quickly. Just going to play this again quickly. Compared to, say, Swift Eagle, which has a lot more sort of gentle feedback from supermassive black holes. So as part of Camels, I ran the Swift Eagle set of these. So we have another 1,000 simulations in this LH set for exploring. So to basically allow us to marginalize over this uncertainty in subgrid prescriptions for galaxy formation. Oops. There we go. There we go. So to kind of to sort of demonstrate the impact of these sorts of these different subgrid models, or at least the kinds of ranges of observables that we're getting for something like Swift Eagle. I'm showing here you have the cosmic star formation rate density we saw already. We also have the halo mass function, the stellar to halo mass relation, and this is just the galaxy stellar mass function. The gray band here is the full range of different observables probed by this Latin hypercube set. And then the other colored lines are other different subgrid models. So one of the promising things, I think, or the exciting things about this camel set is that there may be a way of translating between these different subgrid models. If you think of this large volume of different possible descriptions of galaxy evolution or galaxy formation physics, I guess one of the big questions here is whether these simulation subgrid models live in isolated regions of this space, or do they overlap? And at least in certain areas of this parameter space, it seems like they do overlap. So we can describe the illustrious TNG star formation rate density using some version of the Swift Eagle model, for example. So this provides an avenue for us to maybe overcome some of the sort of model misspecification issues. Okay, so everything we looked at so far has been mostly on these sort of physical properties of galaxies, stellar mass functions, et cetera, star formation rate functions. What we really want to do is be able to compare directly to observations, and so be able to actually forward model all the way over to these observable properties. There's a few different ways you can do this. So at the moment, so what I've shown you so far is doing numerical simulations to some physical fields, and we do some structure finding to obtain some physical properties of galaxies, such as stellar masses, star formation rates, etc. This extra step here, which we call forward modeling, essentially allows us to model the observable properties of galaxies, their broadband photometry, their spectra, etc., and even in some cases all the way to the field level here. So this is often not done as commonly when in these comparisons. Often the opposite is done, the inverse modeling approach, where you compare in this physical properties space. I would argue that we need to do both of these approaches to really get the most out of some of our observational data. So this process of forward modeling the observations requires a number of ingredients. So in our simulations, we have stars, we have gas, we have black holes, and we have to have some prescriptions that then transform this into the observables that we see, right? So we use population synthesis models to model the stellar emission. We have models for dust attenuation and emission. Often, with a range of different complexities, these might be dust radiative transfer codes. We can also take account of photoionization using codes like Cloudy, both for the nebula and the AGN emission, and also absorption within the interstellar and intergalactic medium. And so we can start to model these kinds of data, it's multi-wavelength spectra or imaging data, self-consistently within the simulations. And so one code that we've developed over the last few years to do this is called Synthesizer. Synthesizer is intended to be a fast, flexible, modular, and extensible code for doing these kinds of things. It is not a dust radiative transfer code expensive thing. It's meant to be cheap and quick, so you can start to explore some of the parameters in these forward models. There are a range of different simulation codes that are supported. So if you are using a Cosmos simulation in the room and you're interested, but your simulation isn't listed here, please don't come and chat to me afterwards. And the idea is that we can use all of these ingredients to produce IFU, data cubes, imaging, photometry, spectra, all in a self-consistent way. And the key thing is we can do this for these different simulation sets as well consistently too. So we have the same forward model for each of these codes. I'm happy to talk more about some of the extensions here later on, but essentially with this kind of code, we have these input grids and galaxy components that can then generate all of these observables. And this is an example here of the H alpha luminosity function from the Eagle simulation that we generated using the code. Now, because this is really fast and flexible, what we can do is what we did is we use this to model all of the galaxies in camels. So those 10,000 simulations I told you about before, what we've done is we've run synthesizer on all 10,000 of those. So each one of those has a few thousand galaxies in it. It depends a bit on the cosmology, but essentially this comes to around 200 million sources. So if you wanted to run a dust radius transfer code on all 200 million of those, then that would take quite a long time. Whereas we were able to do this over a weekend, all clock time. So this is an example galaxy from the TNG simulations, showing the generated spectra and the photometric bands. We did this for all 34 snapshots across all these simulations. And what this allows us to do is some quite neat stuff, right? So now we can look at the impact of omega matter on our observables distributions. So this is showing the UV and the R-band luminosity function, the UV and the optical color distributions, and this is the mass to light ratio on the right side. And so you can see the kind of predictable, as you increase omega matter, the number of galaxies increases, so the luminosity function increases. But you also see this impact on the colors. So galaxies get redder in a universe with higher omega matter. This is essentially because galaxies form earlier in a universe with a higher matter density. But interestingly, also this increase in the normalization isn't just due to more galaxies, right? Galaxies actually become brighter at fixed halo mass in a universe with higher omega matter as well. So the actual mass to light ratios increase. Okay, so some interesting results there. What we'd really like to be able to do now is to use these simulations, these expensive simulations, directly within maybe some inference framework. Can we actually learn about these parameters, omega matter, ASM1, etc., directly within an inference framework? And so this is where simulation-based inference comes in. So at the moment, what we have are some simulations. We take some parameters, we run our simulator, we get some data out X, right? So far, I've told you a bit about flares, about camels, and about synthesizer. These are all just simulators, essentially, right? What we really want to do, though, is take observed data and perform inference to understand those parameters. Or we want to compare some observed data given some parameters and choose which model describes the universe better. And so with the magic of machine learning, we can now do this in a much more flexible way, utilizing these expensive simulations. So to kind of set the scene, this is sort of a 1D example of some experiments where you have some parameter theta on the bottom here and some data generated on the y-axis x, right? And what we can essentially do is each point here is some experiment that has been run, or some simulation. Okay, so there's some uncertainty at a given fixed theta. If we follow this red line up, what we're essentially doing is probing the likelihood, right? So if you fix theta, you say what the probability of the data given that parameter, and so you get out this nice distribution. Similarly, if we cut across horizontally here, we get the blue line, which essentially shows us our posterior, right? At the top here, I've put in a very simple sort of prior, right, which essentially cuts across this posterior space. So you can see that for some, more in this more dense area here, if we had some prior on things that we trust, we can actually constrain that posterior a little bit better. But essentially what SBI is doing is it's allowing us to map this space in a more flexible way using neural density estimators. So this is hopefully familiar as Bayes' theorem. What we're essentially trying to do here, there's different flavors of SBI, is to model either different parts of this equation in a much more flexible way. And the one that I'm going to basically concentrate on here is neural posterior estimation. So rather than modeling the likelihood individually here, or some neural ratio estimation, we just model straight to the posterior directly. Now, what this does is it embeds in our prior, but it does allow us to then generate samples from the posterior directly. So what we call amortized inference, which can be a lot faster than having to do the likelihood estimation here plus some extra sampling. And so this is an example using the luminosity functions and colors that I showed previously. So for the Swift Eagle simulation, we took these luminosity functions from the UV to the optical, plus the color distributions, and we asked, okay, can you recover these cosmological or astrophysical parameters from those 1D distribution functions directly? And you can see that it kind of works, right? You get out omega matter, you can measure these supernovae parameters. The AGN parameters less so because of the size of the box. Tantalizingly, some constraints on sigma 8 here. If we look at some of the other simulations, we did this for all 4 of these in camels. For illustrious TNG, we actually get pretty good constraints on sigma 8. The weird thing about this is that these are using just 1-point distribution functions. There's no clustering information in these whatsoever. Whereas sigma 8 is describing the clustering of matter on some 8 megaparsec scales. So how does this work? Well, essentially, where you have a higher sigma 8 universe, galaxies tend to be more clustered and therefore form earlier. And again, what that does, it leads to redder galaxies. So it's the color distributions that are driving these constraints on sigma 8. Now, am I saying that you can go and use luminosity functions to do, precision cosmology? Not quite yet, right? This is a toy model, but I think it shows some interesting applications of SBI to sort of maybe non-traditional distribution functions that could be useful. Are there any questions? Okay, I'll summarize a bit sort of the halfway mark. So I guess the state of play for the stuff that I work on at least now is we've been using flares to sort of break this volume resolution degeneracy. We can also use camels to explore these large parameter ranges, and we can use synthesizer to forward model directly to the observational space, right? But ultimately, what we really want to do is we want to do all of this at the same time, right? So we want to probe down to redshift 0, at high resolution in the large volume regime, and compare directly to observations. So are there ways of doing this?
Maybe I will ask the question at this point. Can you explain how your flares approach here of breaking the volume versus resolution issue? How exactly is that being incorporated into your SBI framework? Is there an advantage of doing that in order to get your procedures that give you better priors, or what's actually the advantage? Have you done it?
The simple answer is at the moment it's not. So but what flares allows you to do is to generate these distribution functions in this large volume regime. Okay. Now, to leverage SBI, you really need this large corpus of training data varying the parameters. That's where camels comes in. So maybe if I move on to the next bit, this might help to motivate it. So please pay attention to the big preliminary side at the top left. So this is still very much work in progress at the moment. But the idea here is I'm going to introduce another simulation set, forgive me, but this is essentially Quixote, which is camels with just dark matter. But these are 1 gigaparsec simulations. So dark matter only simulations, really, really large volume. And there's 32,000 of them varying these parameters. And so what we did is we did an experiment. We said, okay, if we select small regions from these simulations, analogous to like a Zoom simulation, we sample these with different overdensities, similar to flares. Can we use these to then generate these distribution functions for arbitrary parameters? Oops. So this is an example box from Quixote. Each of these is a region that we've taken out from that box. So each one of these regions is 0.013% of the total volume. We then measure some distribution function. Here we're measuring the halo mass function. And we do this for different overdensities. And then what we've done essentially is we've said, okay, if you can build a good emulator for that halo mass function, so this is this phi, conditioned on your cosmological parameters and the overdensity, you should be able to then integrate out the overdensity distribution. So that's this blue curve at the top here. You can measure this from low resolution simulations and get back essentially the global halo mass function from these individual regions. So the top here is showing the halo mass function within each of these small regions. right? And the orange curve here is our normalizing flow emulator for that halo mass function. And the bottom here is showing what happens when we then integrate out the overdensity distribution using that emulator. So this is the global halo mass function for these random parameters here, compared to the true data in blue. So this seems to work reasonably well. So hopefully, yeah, this is essentially a demonstration of this sort of flares approach plus camels. We can then, the emulator we trained, this is written in JAX, so it's fully differentiable. We can then sample, using these the emulator directly. We can do this for arbitrary cosmological parameters. So you can see here the impact of changing omega matter on the halo mass function, sigma 8, the impact on the high mass end. So this emulator can now be used directly within an SBI framework, for example, to constrain these parameters directly. Now, at the moment, the halo mass function is maybe a little bit boring to some of the cosmologists in the room. It's just a one-point distribution function. How can we take this and do this for two-point higher order distribution functions, correlation functions? So Shivan Pandey has been working on this CHARM emulator, which is essentially able to populate voxels of a large field with with halos and with galaxies. And the idea is that you can then measure things like two-point correlation function using just small regions here. So we're exploring at the moment what's the minimum number of regions you need to be able to do this. We also did this for the halo mass function. So we asked, okay, how many regions do you need to be able for this emulator to work? And we find that around 2,000 or 3,000 of these small boxes, or these small regions, is able to get the halo mass function to within 10% accuracy in linear space. And we also find that those regions, once you get to around 50 megaparsecs in size, they're sufficient again to do this. You don't get much advantage from going to larger volumes. So I think this is quite exciting. So what it means is that we could do zoom simulations from these, large volume simulations with arbitrary parameters, and be able to recover some of these distribution functions in this sort of gigaparsec regime for Euclid and Roman, for example. So at the moment, this is the very preliminary work in progress part of this. So we've got a pipeline at the moment which runs a particle mesh cheap simulation using this code PMWD, selects a region from it here, generates initial conditions, and then runs this again with the Swift code. So this is pure dark matter only for the moment. Each one of these is around 50 megaparsecs on the side, but it has Camel's resolution. So we're at 10 to the 7 solar mass resolution. So we're resolving halos down to 10 to the 9 M solar. Just to emphasize, so this with Quixote, just using these small regions, we could only probe down to 10 to the 13 solar masses. So this is the promise of this technique, right? So this is what we're able to do with just Quixote. If we can push down to this 10 to the 9 M solar regime, then we can probe all of these halos here down to sort of another 4 orders of magnitude lower. So yeah, this is very much work in progress. If any of this sounds kind of interesting or exciting, then please do come and chat to me afterwards. This may be another opportunity to ask us any questions or concerns. Yep.
So at this point, are you still only at Redshift 5, or are you able to evolve your simulations with time?
This is all Redshift 0.
Okay.
So using Quixote, at least, we are able to take these regions at Redshift 0 and generate this halo mass function at that Redshift. So yeah, we're getting these 10 to the 15, 10 to the 16 M solar clusters. Some of the Quixote parameter variations are quite extreme. So you end up having these 10 to the 16 M solar clusters and things, but we're actually able to still capture that variation, at least in the halo mass function.
Thank you.
So you mentioned you like select different regions for the zoom ins, right? So for example, coldest regions. Is it like optimal way to select the region? So does the algorithm tell you where the most information is?
So at the moment, we do a sort of stratified sample in percentile overdensity. This is, I think, clearly not efficient, but it does allow us to get a large range of different environments. Max Lee, who's a graduate student at Columbia, has been working on this carpool GP active learning approach to essentially ask, okay, once you have 500 of these regions, where should I sample next in parameter space or overdensity space to best improve my emulator? So yeah, he's been working on that for a few years now, and we're hoping to apply it to this. The open questions are which distribution function do you want to optimize against? So we're talking about the halo mass function here, and like I implied, a lot of people probably don't care about the halo mass function. So which ones do you optimize against, and how can you build these sort of Gaussian process emulators in that space that you care about? So for some of these clustering statistics, that might be a little bit more tricky. But yeah, any ideas? Welcome.
Yeah, just the size of the region that you zoom into depend on the over density amount. I mean, that's something that looks like it'll be a cluster compared to something that would be a group, you know, that sort of thing.
So at the moment, what we've done is we've chosen a fixed size. So for something like the halo mass function, volume normalized, this makes measuring that distribution function nice and easy, right? Because you essentially have the overdensity on a fixed scale. What that does mean is that every single region has a different particle number. So when it comes to actually running these things, it becomes a little tricky. So for a lot of these things, you know, lower than median overdensity, they're very cheap. They're very, you know, very low particle numbers. You can run them very, you know, in a few hours. For the more massive things, these are going to take longer. And they're a bit, you have to do a bit more hand holding. An alternative approach would be to use a fixed particle number and just change the size of the region. What that does then mean is that you have different volumes, right? So it depends what you want to use these zooms to do, and what kind of emulators you want to train. It may be that for some use cases that's sufficient, and then that would become a lot easier to manage. I think for the moment, especially where we care about, you know, ignoring the emulation side, this is also a great suite for just understanding the environmental dependence of, you know, halo formation and galaxy evolution. So I think having these fixed volumes, I think, makes that kind of comparison as well quite easy. So you could look at the outskirts of some massive halo, for example. Okay. So we've got like 20 minutes left. I was going to take a bit of another curveball now. And so we talked so far, not just about Synthesize, but about the forward modeling. So going from our physical theories to the observations and various ways of achieving that. One thing I just wanted to talk a bit about at the end is this project we've done to do the opposite, so the inverse modeling. So actually fitting observations to get back physical properties. You may know this is SED fitting. So this is a project that's been led by a graduate student at Manchester, Tom Harvey. He's now started a postdoc. But essentially, yeah, how do we determine the properties of this galaxy that we may have some, you know, relatively sparse sort of information on the photometry for? And so there's a whole industry of codes and approaches for doing this, right? So some of these codes on the left could be used to fit both photometry or spectra. This is an example from a prospector showing as you increase the photometric coverage that the posteriors here on your properties are better constrained using a nested sampling approach. Some of these just use a simple maximum likelihood estimator, so you don't get those uncertainties, but they are very, very quick. But what we'd really like to be able to do is to do a full Bayesian approach for these kind of upcoming wide field surveys, right? So unfortunately, things like Euclid and Rubin are going to observe billions of galaxies, and so fitting some of these, you know, individual objects that takes, you know, a few minutes or hours to do for each one is clearly not going to be feasible. And ultimately, understanding this galaxy formation evolution is now not really limited by the number of galaxies, right? We have these huge samples. It's actually limited by our methodologies for analyzing those galaxies. So this is using synthesizer under the hood. So what we can do is we can build up a mock galaxy using synthesizer, using these different ingredients here. And we can use this within these sort of inverse modeling approaches as well. So I'm going to switch to Tom's nice slides because they're better than anything I could have done. Hopefully this works. Oops. Great. Hopefully. Yeah. So what we can do is we can use synthesizer to generate a giant sort of training set here, essentially for a simulation-based inference approach. So we define some components, we vary things like the dust attenuation, etc., and we generate millions of these fake galaxies. So these are relatively simple forward models of galaxies. These aren't using the detailed numerical simulations. These are using parametric models for their star formation histories or for their dust, etc. But we can essentially create mock galaxies that look, that cover this parameter range reasonably well. That parameter range being stellar mass, star formation rate, the attenuation, the metallicity, etc., etc. And we're generating observations here. These are 14 fluxes across 14 photometric bands. And then what we do is we train this SPI model. So this is a neural posterior estimator again. If you're interested in the details here, I can chat later, but we essentially do some full optuner hyperparameter optimization of this and settle on this sort of final model architecture. The reason for doing this, so adding another code to this whole corpus of different codes, we have essentially this link to synthesizer where there's nice flexible code under the hood, and we have this sort of speed from using SPI to get amortized inference, which I'll get onto in a second. So this is some examples of the inference from photometry. This is here comparing to a traditional sort of SED fitting code called bagpipes, showing that we recover things like stellar masses. There's some slight differences here in sort of mass-weighted ages, which bagpipes isn't the ground truth here, but we're essentially able to recreate something like bagpipes. And this is showing some example fits to galaxies. So from a sort of test set comparison, showing the diversity of different galaxies we can fit with this approach. So again, these are some examples and some posteriors here on these different parameters, as you kind of saw previously from Prospector. What we can also do is do redshift estimation. So if you care about distances, etc., or for cosmology, this is showing the true spectroscopic redshift against the one estimated from this code's inference, compared to a code called EASY, which is literally designed purely for redshift estimation. What we do is we actually get less biased results compared to EASY, but we also get the full posteriors on all of those other parameters for free as well.
Where is the EASY result here?
Sorry, so the yellow here is basically the outlier fraction, NMAD. It's just completely gone. Yeah, and the bias here from using EASY compared to inference. And so, we achieved similar sort of results here to this approach, which is using
all
just
you have
maximum.
here is the photometry and you're estimating redshift.
Exactly, yeah. So the estimation here is on the y-axis, and then the truth here is essentially on the x-axis. This is an example test that we did where we sort of basically systematically removed bands to show how well robust our redshift estimation was. And it seems to be, again, still pretty close to the one-to-one line. The overall bias doesn't increase too bad.
There's a question online as well. Braden, I don't know if you can unmute yourself or you want me to ask it?
Hi, can you hear me?
Yes.
Yeah, I just noticed on your physical parameters, a lot of them seem to kind of follow a nice linear trend, except for your AGN parameters. So I was wondering if you had any idea as to why AGN parameters seem to not follow as nice as the other parameters did.
Sure, so this is on the Camel's inference stuff?
Yeah, right before your slides.
Yeah, so the main reason for that is the size of the Camel's boxes that was used to do the inference. So So that was an example done with the sort of first generation camels, which is 25 megaparsecs on the side boxes. So unfortunately, because they want to run thousands of these simulations, you're really limited in both the resolution and the volume. As a result, you simply don't have the massive halos that where AGM feedback is most predominant. So unfortunately, the impact of AGM feedback is low. So the observable impact is also low, and so the inference doesn't really work in that regime.
So when you get more data and such, you hope that they'll start to converge kind of like the other ones do.
So ideally, with the sort of zoom approach I was talking about, we will explicitly model those kind of halos. Yeah. So we would, with a camels-like suite, but with zooms, we could target those overdense regions where there are, where the impact of where there are massive halos and where we can see the impact of the AGM feedback more directly.
Great, thank you.
I guess what I want to do is kind of skip ahead a bit to this plot to kind of make the point here. So this is showing the speed of the inference for a few of these different traditional techniques compared to inference. The far right here is Prospector, which is a full nested sampling approach to doing SB fitting, which for each object can take of the order of 10 hours for some objects. Bagpipes, which I talked a little bit about before, is of the order of minutes. So this is a MCMC approach, typical Bayesian approach. Easy here, the one I talked about before, this is maximum likelihood, so it's super quick. You don't get full posteriors. Using inference, at least this is for two different ways of doing the neural density estimation, neural spline flows, and mixture density networks. We're now, comparable speed to easy, but getting full posteriors. The dashed line here is a very fake kind of comparison here, but essentially is the number of objects that will be detected by Euclid per unit time over the next sort of 10 years. So if we were going to process Euclid with a single laptop with a single CPU on it, right? This is the rate at which we need to be fitting those galaxies to be able to do any science. That is not the case, okay? We do have more compute than that, but I think it's a nice way of showing that even if we did that and we did it, if we do this once for Euclid and we don't vary any of those underlying parameters, using these traditional approaches is going to take a long time. Whereas with inference, we can do this and we can do this multiple times and explore some of those model dependencies.
Does your inference time include the amount of time it takes to simulate the galaxies, or is that separate?
Good question. Yeah. Very, very unfair. At the moment, this doesn't include the simulation time.
Okay.
Within synthesizer, that's pretty quick for these parametric models. We're talking a few hours to do, and you only do that once, right? Now, if you do want to expand this space and probe different observables, for example, you would have to regenerate that training set. So you're right, there is an upfront cost. Sure. So I was just going to go back quickly. There's a few different sort of applications, I guess, of this that's enabled by the, oops, is this going to work? No. Okay, well, you miss out on the nice animation, but it is quite cute when it does work. Here we go. There we go. So the main reason I was trying to get that going is for resolved properties of galaxies, right? So because we now have this very, very rapid fitting procedure, we can now do pixel by pixel fitting. So this is showing, Tom made this, I can't take any credit, but it's quite fun, showing different intrinsic properties of this simulated galaxy plus the fits to it. So you can see metallicity maps, attenuation maps, etc., etc. So you can then do this, but then with full posteriors for each of those parameters on each pixel. And one of the things we're looking at a bit at the moment is how you incorporate the information from multiple pixels or from neighboring pixels effectively. But this is, I think a really exciting approach for doing these kinds of resolved studies. Another thing that is obviously hopefully super exciting is that our simulator can generate spectroscopy, so we can also fit spectroscopy. There's obviously some added issues here in terms of how you compress that feature space vector down to enable you to do effective SPI. So we're looking currently at a few different approaches here. There's some work from sort of Peter Melchior and Changyun Han who've done some work on autoencoders for reducing the dimensionality of this spectra. But what this also opens up the opportunity to do is to look at sort of much more what we call complex emission models. So within synthesizer, we can also model the AGN emission directly. So both the narrow line, broad line, torus, et cetera, et cetera. And we can start to now modify many of these parameters in the forward model and actually start to constrain them, perhaps using this population level data. So again, this is somewhat work in progress at the moment, but I think it's very, very exciting. And then finally, one of the things I talked about with SBI a bit was, we not only want to infer these parameters, but we want to do model comparison. And so there's a few different approaches now for doing this. One of these is evidence networks. So this is an approach proposed by Ben Vandal and now Jeffries at UCL. But essentially what you can do is use your posterior samples from two different fitted models to ask which model better fits the data. Okay, so this is an example here of calculating this sort of Bayes factor using two different SPS models, right? So this is a model including the effect of binaries and one without it, essentially asking which one benefits the data. This is an example, quite an exciting one, I think, over the last few weeks with some of the recent results, asking whether some of our POP3 models better fit the data or traditional or POP2 models. So yeah, early POP3 star formation, we have some models that predict the emission from these objects. We can now start doing these sort of model comparison tests on a pixel by pixel level for these kinds of populations. One of the big limitations with SBI is that you do have to have a fixed input vector. So you have to choose the observables you want to fit, and then generate your training corpus and train your model. If that changes, or if you have a more heterogeneous set of data, then SBI is quite brittle to some of that. So related to your point, I guess. One approach for getting around this is SimFormer. So essentially using a sort of attention mask approach to turn on and off features in your input vector. Again, this paper only came out a couple of years ago, but is hopefully one approach we've been looking at to sort of overcome this and make some of this SBI framework a bit more flexible. There are other approaches that you can do, so using your priors and simply sampling from them multiple times, but those sort of reduce some of the speed of the original approach. So I'll kind of basically finish there. I realize I've talked about a lot of stuff, so I apologize on that front. But hopefully there was something of interest to you somewhere in there. Here's a sort of overview of this. But the last thing I did want to advertise was that we're doing a meeting on SBI for galaxy evolution. We've been doing this the last couple of years in Bristol. This year, in a few months' time, we'll be doing the next one in Cambridge in the UK, the other Cambridge. And June 23rd to 26th, registration will open on Monday if I can get the payment link set up. But if you're interested in joining us, unfortunately, abstract submission is closed now. But if you're still interested in joining us, we have a really exciting program of talks, tutorials, and discussion sessions. So please come and chat to me afterwards if you're interested. Thank you very much.
Thank you, Chris. Questions for Chris? John.
What wavebands do you have supported in like the synthesizer? Like I saw a few of them, like a few of the instruments and wavebands, but what wavebands do you have supported and what wavebands do you want to support?
So the simple answer is whatever you want. The more complicated answer is that not 5 red. So synthesizer is not a dust radiative transfer code. So we don't self-consistently model the attenuation and the emission from dust. We have some sort of gray body, black body emission templates that you can use. We're also working on a sort of energy balance approach. So based on the attenuation of UV optical, you can then link that to the emission in far infrared. But these are toy models. So I would say that, you know, in the UV optical, we are, you know, the methods we are using are pretty robust, but beyond the sort of near infrared, we're working on some approaches there. We don't do anything in, you know, the radio or sort of the X-ray side of things. There is a student project looking at how we could do radio modeling within synthesizer. This is in very early days for the moment.
Thanks, Peter.
So, one mystery from Hubble and JWST is about the numbers of galaxies at high redshift, the numbers of massive galaxies. Is there potential here for you to study that and so on as well?
Yeah, so a few years ago, I used this approach called extreme value statistics to sort of evaluate where galaxies lie in terms of their mass and redshift and whether there's any tensions with lambda CDM. So I think 2022, 23, there was maybe a bit more excitement about some of these, you know, very extreme objects. I think that started to go away once, you know, we took into account some of the recalibration. I think the new tensions here are in passive objects, you know, some of these things that seem to be forming very, very early. I have been working with a student to do that extreme value statistics, but rather than in the sort of stellar mass redshift plane, but in the observable sort of, you know, flux versus redshift plane or luminosity. So actually forward modeling those galaxies and saying, okay, this is the brightest galaxy we expect to see at redshift 10. Now, that, you know, essentially using synthesizer to do that, you have to be then a lot more explicit in your forward model or the assumptions that you make. So it's unclear to me, you know, whether that's helping or just providing another way, another avenue of confusion in this space. But it's interesting at least to say, you know, to make some of these statements and what, you know, what they rely on. Yeah, happy to chat more afterwards.
Yes.
As an observer, Synference and SVI is really exciting. Not only am I able to model observations, but I can just see a lot of utility in writing proposals and whatnot. A question that I have is during your step of initializing your galaxies kind of analogous to making a template set, how much control do I have over that if I were to use Synference? To give an example, I was writing a proposal to where I needed to get a photometric redshift of a galaxy. You know, it's very AGN dominated, but none of the templates I was using for easy really took into account that. So would I be able to turn up the AGN knob, so to speak?
Yes. So I forgot to mention that synthesizer, Synference is all open source, and we've tried to make all of the ingredients that go into these models open source as well. So we have different grids for the stellar emission. We have a number of grids for the AGN emission that you can go and download now and start to play with. So you can build a synthesizer forward model, including the AGN, and, you know, have a AGN on and off knob if you want. What I would say is that AGN model in synthesizer is still quite, you know, immature and young, right? So we tried to build something super flexible, kind of with SPI approaches in mind. You know, in some sense, I don't care what the right model is. I just want a model that's flexible enough to perhaps encapsulate the truth and allow me to learn something. So I think, yeah, we're in conversation with people who are more experts in some of the AGN modeling to try and improve that model. But yeah, right now you can go generate a data set and train the SPI Synference approach and do some fitting. I just say the caveat being that, yeah, that AGM model is maybe not the most sophisticated compared to some out there now.
Thank you.
All right, I'm afraid we're out of time, so let's thank Chris again for next talk. Chris is here today. Be brief 04